Last time we saw that when X is a Noetherian topological space, it has an irreducible decomposition, can be written as a union of closed irreducible subsets. And now we want to get back from this general setting to the setting of affine varieties. So when X is such an affine variety, and it is described by the ideal I inside this polynomial ring, then the concrete question you can ask is, how do you actually compute this decomposition here in practice? And the answer again comes from commutative algebra, because the claim is to compute this, you should just take the ideal I and compute its primary decomposition. So for this, let's recall primary decomposition of an ideal I means you write it as a finite intersection of ideals Qi in this ambient big polynomial ring. And these Qi's are primary ideals, which means there are proper ideals inside this polynomial ring, such that they have a kind of curious property that if you have a product A times B is in one of the ideals, it means that A is in the ideal or some power of B is in the ideal. It's a curious mixture between being a prime ideal and being a radical ideal. And the precise interaction from this kind of definition, what you can see is that if you have a primary ideal Q and you take its radical, then that radical becomes a prime ideal. So in other words, we also get from this primary decomposition a collection Pi of prime ideals. And then this, we can actually kind of use this to upgrade a bit our primary decomposition using something about I. Namely, what we know is that the ideal of such an affine variety is always a radical ideal, which means I is the radical of I, and then, well, we take such a primary decomposition, we plug it in here, and then it's a kind of short lemma for you to check that the radical of such a finite intersection is the same thing as the intersection of the radicals. But then these were given this new notation Pi, and so we can actually write I not just as an intersection of primary ideals, but because I is radical, we can also write it as an intersection of some prime ideals. And now we're getting closer to this irreducible decomposition because, well, the set X is by the Nullstellensatz the vanishing set of its ideal of functions or ideal of polynomials vanishing on it. And I is then an intersection of these ideals. And the vanishing locus of an intersection was the union of the corresponding vanishing loci. Intersection becomes a union, and then we have written indeed X as a union of vanishing ideals of prime ideals. And we have seen one of the earlier parts that the vanishing locus of a prime ideal is exactly an irreducible subset of AN. So we have written X as a union of irreducible subsets. So we set Xi to be this vanishing locus, and then it might be that one of the prime ideals actually occurs several times, and we can remove that if this occurs. So after removing, and it could also be that maybe it doesn't occur several times, but maybe some of the primes are not minimal, which means that some of the vanishing loci are not maximal with respect to inclusion. After removing them, we obtain unique irreducible decomposition. So the upshot of this part here is that to get the irreducible decomposition, what we should do on the commutative algebra side is the primary decomposition. And in a certain sense, this again justifies why the primary decomposition on the commutative algebra side is a nice thing to consider, because it allows us this kind of more geometric decomposition of closed subsets. And another angle which you can have is that when X is an affine variety, you get a second description of the irreducible components xi of x, because these are precisely the maximal irreducible subvarieties of x. Maximum here again with respect to inclusion. So, and I give this as an exercise. I think it's a good exercise because it recalls all of these notions of being irreducible, and it also recalls some properties about this irreducible decomposition, because the hint is you should use the uniqueness part of the irreducible decomposition to see that indeed the maximal irreducible subvarieties are exactly the irreducible components. And so kind of with this exercise, we can then have a nice corollary, another classification of the irreducible components of X. Before we talked about things relating to the ideal, but then, as it is always the case, we can also relate it to the coordinate ring, or the ring of polynomial functions on X, because the claim of the corollary is that the irreducible components of X, if you take their vanishing ideal in AX, then they exactly map bijectively to the minimal prime ideals of A of X. And the proof is also not so hard, because, well, the irreducible subvarieties of X that we have seen before by this map exactly map to the prime ideals here. And this is an inclusion reversing correspondence. And so in particular, the maximal irreducible subvarieties of X map to the minimal prime ideals. And by this exercise, the maximal irreducible subvarieties are just the irreducible components. So here we have seen when X is an affine variety, the irreducible components on the one hand can be computed from the primary decomposition of the ideal, and in terms of the coordinate ring AX, they can be computed as the minimal prime ideals of this ring.